right, so let's take a look at 3.1, part 2. Okay, so we'll finish that up. That'll be pretty quick. And then we'll look at 4.1, the first part, and we'll finish 4.1, the second part tomorrow. All right, so let's take a look at something like this. If I did the inverse sine of the sine of 12 degrees, we'll look at what we think would happen. It's kind of like if I did this. 5 squared, square rooted. What would happen if I did 5 to the second power and then took the square root? It just cancels. Right, because this function is the squaring function. Then it's combined with the square root function. Those two functions are inverses. They cancel each other out. And you basically get back what you started with. So we're taking the sine of 12, and then we're taking the inverse sine. So what answer do you think I would get? 12. All right, so let's try it. Let's take the inverse sine of the sine of 12. Hit enter, and you do. You get back 12. How about if I did the inverse sine of the sine of negative 47? What do you think I would get if I type that? We get negative 47. Now, yesterday we talked about two numbers that we had to stay between when we used that chart for inverse sine. Anybody remember what the two angles were? Yeah?
Between negative 90 and 90.
Between negative 90 and 90. So let's see what happens if I try a number here that's beyond negative 90 and 90. Let's try 94. So that's not between negative 90 and 90. And I did not get back the same answer that I plugged in. So the idea of these two things canceling each other out will work as long as you stay between negative 90 and 90 for what you plug in. So that's our first formula. Inverse sine of regular sine cancels each other out. And the answer that you get is whatever you typed in to begin with, as long as what you typed in was between negative 90 and positive 90. Or, if you were doing radians, that's negative pi over 2 to positive pi over 2. Okay, you go bigger than 90, smaller than negative 90, doesn't work. Because the calculator is built, the calculator is programmed to always give you an answer between negative 90 and 90 when you do inverse sine. Always. Can't give you an answer outside of that. All right, so now, let's look at something slightly different. Let's look at this. They look almost the same. Does anybody see what the difference is?
They're just sine and then the inverse sine is just flipped.
Yeah, so it's really an order of operations. Which one are you doing first? It's kind of like I take 5, square it, and then take the square root. Or if I take the square root of 5 and square it after. That's the same thing. You're still squaring it, and you're taking the square root of it. The order, well, doesn't matter. So here, these two things are still going to cancel out. So when I type that in, sine of inverse sine of 0.3, what would you expect that I would get? 0.3. Yeah, I do. I get 0.3. Okay, we do another number like, let's do negative 0.78. What do you think I get when I hit enter here? Negative 0.78. Yep, I got back exactly what I typed in. Now, yesterday I tried a bunch of numbers here. I showed you guys all different numbers, and I think I put them on the board. Does anybody remember the highest that I let this number go? Inside here?
1.
1. Yeah. I told you when I tried to go above 1, I think I did something like this. I tried 1.001. It didn't work. You can't go above 1. And what didn't I go below?
-1?
-1. Yep. So this formula, we'll call it formula 2b. That's when the inverse is on the inside. The sine of the inverse sine, they cancel each other out. And the answer that you get is exactly what you started with. As long as you started with a number between -1 and 1. But this time, if you plug in something that's not between -1 and 1, you won't even get a different answer back. You just won't get an answer at all. Okay. In formula 2a, you got an answer no matter what. Whatever you fill in here, you will get an answer back. But in 2b, you won't, unless you stay between -1 and 1. Okay, any question on that? So that's when sine and inverse sine cancel each other out. Let's look at cosine and inverse cosine. Actually, I think that's going to be, oh, that'll be the next one. All right, so let's try some examples, and then we'll do the next one. All right, the inverse sine of the sine of pi over 8, will that equal pi over 8? So the answer here is basically yes or no. Which one is this one more like? You got inverse sine, then regular sine. Is it like 2a or 2b?
2a.
Right, it's more like 2a. The inverse comes first, and then the sine is on the inside. What does formula 2a say we have to stay between?
-90 and 90?
-90 and 90 in degrees, and in radians?
-pi/2.
-pi/2 to pi over 2. All right, so this is the range of good things. We got to be in here. Pi over 8. Here's 0. Where does pi over 8 fall? On that number line.
Down there. Outside.
So pi over 8 is bigger?
No,
pi over 2
shortly
is
after
smaller.
the 0.
Yeah, it's smaller than pi over 2. It's a smaller number, but it's still a positive number. So pi over 8 might be like right about there. It's closer to 0. So is it between the two numbers that it needs to be?
Mm-hmm.
Yeah. So is that going to work? Yes. The answer there is yes. Okay, so it's a yes or a no. How about, let's look at this one. The inverse sine of the sine of 3 pi over 2. Well, inverse is on the outside, so it's the same picture. We got to be between -pi over 2 and pi over 2. Where's 3 pi over 2?
Outside of it?
Which way? Is it smaller than -pi over 2 or bigger than that?
Bigger.
Yeah, it's triple pi over 2. So that's way outside what it's supposed to be. So if you type that in, are you going to get back what you started with? What do you think? No. You will get back an answer. Okay? You'll get an answer, but it's not going to be what you started with. So no, that one doesn't come out right. All right, let's try this one. Okay, what's different here?
Sine and inverse sine are flipped.
Yep. So now you get the inverse on the inside. When inverse is on the inside, what are we supposed to be between? -1 and 1. Is the number we plugged in between -1 and 1? No. If you type that in, will you get a different answer back, or will you not get an answer?
You won't.
Yeah, you won't even get an answer. It's going to be an error. You can't do that. All right. How about the sine of the inverse sine of 0.6? Will that equal 0.6?
Yes.
Yeah, because it's between -1 and 1. Yep. So any question on using those formulas? Okay, yep.
Can you scroll up a bit? Yeah.
So the other way you could see the question worded, instead of a yes or no, you could say simplify, and then it would say like the sine of the inverse sine of 0.6. If the question says to simplify, don't put yes. That doesn't work. Okay. It's like me asking you what time it is, and you say yes. Okay. So sine of inverse sine of 0.6. What would that simplify to? 0.6. Okay, I wouldn't give you one to simplify that you can simplify. Right. So any question on the difference between like the is something equal to something versus simplify? Okay. Right, so let's look at inverse cosine. So, just like inverse sine. Inverse cosine and regular cosine cancel each other out. You'll get back whatever you started with, as long as you started with something between two numbers. When we used the table yesterday, what did we always have to stay between for the angle?
0 to 180.
0 to 180, or in radians?
0 to pi.
0 to pi. Yep.
That's close.
So this is the one that if you type in something beyond 180, you will get an answer back. It just won't be the one you started with. Right. So now, what do you think? What do you think is going to be different in Formula 4b?
They're going to be flipped around.
Yeah, it's just which one are you doing first? You're doing the one in the parentheses first. This time we're going to do the inverse first. And we're going to do the regular one on the outside. All right. When we did Formula 2b, what number did we have to be between?
-1.
And that's the same here. The reason why it's -1 to 1 is because, we're going to learn more about this picture next week. But if I graph sine and I graph cosine, I graph both of them. Okay, there's sine, that's in blue. Look at how high and low it goes. And now watch when I draw the red one. That's cosine. And look at how high and low that one is. What's the highest that the blue and the red one go?
Up to 1.
They go up to 1. And what's the lowest they go?
-1.
-1. That's where those two numbers come from. Has to do with how high and low the graph goes. It doesn't go beyond 1 and -1. So when you do something like 1.5, you're essentially asking this question. Tell me where that line crosses those waves. Where does that line cross those waves? It doesn't. It never crosses them. That's why this doesn't work. It never crosses. So let's try a couple of these. All right. Is that one like 4A, or is that one more like 4B?
4b.
It's like 4B. Yep. What's the value you need to stay between?
-1.
-1 and 1. And what is our value between those two?
Yes.
0.95. Yep. So that will work fine. How about this one? Inverse is on the outside. What are we supposed to be between when it's on the outside?
0 and 180 or 0 or pi.
Yeah, so either 0, in this case we're using degrees, so 0 to 180. Are we between 0 and 180? Nope. So that one's not going to work. Okay. Any question on that? Alright, so let's look at the last one. Inverse tangent and regular tangent cancel each other out. You'll get back whatever you started with. As long as you are between, what did we have to be between yesterday? I think we did inverse tangent.
-90 and 90.
Okay, any difference between that and inverse sine? Because that's what inverse sine is
Can't be
also.
equal to.
Right, it can't be equal to. Yeah. So inverse tangent, you got to be between -90 and 90, but you cannot equal 90. Remember, we looked at the chart. When you go to 90, the tangent on the chart, it said undefined. Okay, so can't do 90. All right, let's think about formula 6b. Okay, I've been trying to kind of show you guys the connection between the restriction on the second formula. And the restriction on the second formula always has to do with how high and low the graph goes. So for sine, it was -1 to 1. Cosine is also -1 to 1. Let me graph tangent and see if you can tell me how high and low that one goes.
I don't know if this matters, but how did you get those to go wavy? On the thing. I'm just asking because mine doesn't do that.
You have to change your zoom. I did zoom 7.
Okay.
We'll talk more about that.
Alright.
Yeah. All right. So here's tangent. Well, it's not a wave. It is a repeating pattern, but it's definitely not a wave. How high and low does it look like that one goes?
In both directions.
Yeah, it goes from infinity to -infinity. And this graph has a bunch of something we've talked about earlier this year. What do you think this graph has a bunch of? And they repeat. No quadratic equation.
I forgot what it's called. It's when like a line is infinitely going towards a point and it can't reach it.
Okay. What do we call that?
Asymptote.
An asymptote. Yep. So tangent is a very different looking graph than sine or cosine. It has a bunch of vertical asymptotes. So it'll get closer and closer and closer but never reach it. And the asymptotes repeat at regular intervals. What is that regular interval they repeat at? Well, we're going to talk about that next week. But the point here is it goes up forever and it goes down forever. So, what do you think I'm going to put for my restriction on x here?
-infinity to infinity.
Yeah, which effectively means there is no restriction. X can be any real number, and this formula always works. Okay, so when the inverse tangent is on the inside, shouldn't even think about it. Okay, always works. So, is the tangent of the inverse tangent of 30.4 going to equal 30.4?
Yes, it will.
Yes. Of course, because it's formula 6b. Inverse is on the inside. And that number is definitely between -infinity and infinity. 30.4. Okay. So any question on that? All right. So that'll be the first part of the homework. You'll have maybe 7 or 8 of those. And you just have to say yes, it would work, or no, it wouldn't. All right. And the last thing for this week. Right triangle trig. So we're going to be doing trig like we did on the unit circle, but we're not using a circle. Okay, we're going to use a triangle. So it's the same concept, just a different way of visualizing it and thinking about it, but it's still the same thing. Well, if we're going to use a right triangle, first thing is we need to know what is a right triangle. what makes something a right triangle? Yeah.
A triangle with a 90-degree angle.
Okay, it's a triangle that has a 90-degree angle. Okay, so a right triangle is a triangle with a 90-degree angle. Across from the 90-degree angle is the longest side. It's always the longest side. And that has a special name. Does anybody know what you call the long side in a right triangle?
The hypotenuse.
Yep, the hypotenuse. And does anybody know what you call the two short sides? The legs. Yep. So this little square in the corner right there, that's the symbol for a 90-degree angle. Two short sides are the legs, and the long side is the hypotenuse. Okay, so let's look at that angle and that angle. Okay. What kind of angle is this one that I circled in red? That's a 90-degree angle, which we call a right angle. What do all the angles in a triangle have to add up to?
180.
They all have to add up to 180, and everyone agrees this one's 90, right? Okay. What does that mean these other two black angles have to add up to, the ones that are circled? They also have to add up to 90. So if this was like angle 1 and angle 2, angles 1 and 2 have to add up to 90. What does that mean about them? Yeah?
They're complementary.
Yep, they're complementary. And there's another word. So together they are complementary. How about by themselves? What kind of angle does that have to be?
Acute wave.
It has to be acute. Yep. So an acute angle is always what the other two angles in a right triangle are. Since one of them in the corner is already 90, the other two have to be less than 90, but they also have to be more than 0, or you wouldn't have a triangle. Okay. So that's what an acute angle is. Less than 90, greater than 0. Now, one of the things we're going to have to figure out is how long each side is in the triangle. As long as you know two of them, you can find the third one. Any two. A leg and a hypotenuse, or both legs. Does anybody know the name of the formula you can use to find the length of the sides of the triangle?
Pythagorean theorem.
Yeah, Pythagorean theorem. And what's the formula for that?
A squared plus b squared equals c squared.
Right. And can you explain what that means?
So you.
Because I don't have an A, a B, or a C in my
A
diagram.
and B are the legs.
A and B are the legs.
C is the hypotenuse.
Yes.
Never used that.
Yeah. So whether you call it X, Y, Z, A, B, C, the letters you use don't matter. It's the idea of the theorem. If you take one leg and square it, plus another leg squared, you get the hypotenuse squared. That's the Pythagorean theorem. Now, the Pythagorean theorem, it only works in triangles that have a 90-degree angle. So when we eventually look at triangles like this, the Pythagorean theorem doesn't apply. Because to use the Pythagorean theorem, you've got to have a hypotenuse. To have a hypotenuse, you've got to have a 90. That doesn't have a 90. So we'll talk about what we would do in a couple weeks on that kind of problem. All right, so we're going to define the 6 trig functions again, just like we did on the unit circle. So last week we had sine. It was what? Cosine? Does anybody remember what cosine was?
X.
X. And then tangent was
Y over
y over x. That's how you define the trig functions on a unit circle. We're going to do the same trig functions again, but we're going to look at it in terms of a triangle instead of a unit circle. But there's 2 words that we're going to use. Well, actually, there's 3. We're going to use the words opposite, adjacent, and hypotenuse. Okay. That's going to be in place of writing a coordinate. We're not going to talk about sine is y and cosine is x. That's unit circle. Okay, we're going to use these words instead. So first, let me just kind of explain what opposite and adjacent mean. So opposite and adjacent, those are what we call they're relative terms, meaning they are dependent on which way you are facing. Okay? Kind of like the words left and right. Okay? You couldn't like put a sign in this room on a wall and label it left or right. It's not like there's one wall that's always left. It all depends which way you're facing. Okay? So the way that they tell you which way you are facing is they mark an angle with a Greek letter. For this triangle, pretend like you're standing right where that letter is and you're looking out. The side that you'd be looking out that's furthest away, that's opposite. The side that's right next to you, okay, or that's what adjacent means. Adjacent is right next to you. In this case, is the bottom. Now the hypotenuse is always across from the 90. That never changes. Okay, an example of a word that's kind of like that would be like up. It doesn't matter if you face this way or you face this way. Up is always towards the ceiling, no matter which way you face. Hypotenuse never moves. Now, you take the same triangle, but change your perspective. Your perspective is always one of the acute angles. It's never the 90. Never. Okay. Hypotenuse would stay right where it is. But if your reference point is at the top of the triangle, if that's the angle that you're referencing, where would opposite be now?
On the bottom leg?
Yeah, opposite is the side that's furthest away. It's basically the side that if you erased it, it would have no effect on this angle at all. I still have an angle right there. Nothing changed. Okay, so opposite this time is at the bottom. And where would adjacent be? Yeah, it's the side, it's the height in this case. It's right next to it. Okay. Adjacent is the side that if you erase it, you don't have an angle anymore. If I erase that side, my angle's gone. Now it's open. Okay, I don't have an angle. Okay, so opposite and adjacent can switch places. Is there any question on that? Okay, and they'll always mark the perspective with a Greek letter. What Greek letter is that?
Theta.
Theta. Theta. Yep. Theta. So opposite, as I said before, that's the side in the triangle that is not part of the angle at all. It's the side that's farthest away from it. If you erase it, it doesn't affect the angle. So it's the side that is not part of the angle. Versus adjacent, that's the side in the triangle that is one of the sides of your angle. If you erase it, you don't have an angle anymore. And the hypotenuse, that's the easy one. That's the side that's always across from the 90. All right, so now, using those three words, opposite, adjacent, and hypotenuse, we can write the 6 definitions of the trig functions. Start with the 3 on the left. What are the 3 trig functions I usually put them on the left side?
Sine, cosine, tangent.
Sine, cosine, and tangent. Now, first of all, each trig function is going to be a fraction. It's going to be a fraction of one side of the triangle divided by another side. For sine, it's the length of the opposite divided by the hypotenuse. And let me write something as I do it. Okay, I think some people might have heard this before, but sine is opposite over hypotenuse. Sine opposite over hypotenuse. The cosine is adjacent over hypotenuse. Cosine is adjacent over hypotenuse. And then the last one, tangent, is opposite over adjacent. Has anyone seen that before?
Yeah.
Yeah, it's just a way to remember.
Gary 5, yeah.
Mr. Fartolia? Yeah, Sakatilla. Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. So I had asked one year if anybody knew a way to remember it. And I got, instead of Sakatoa, I got Sacagawea. So Sacagawea is not quite going to help you. Remember that. You know, she did something else. She was an explorer or something. But she's not in trig. Not that I know of. So Sakatoa.
Lewis and Clark.
Yeah. I think somebody just got confused. Sacagawea, Sakatoa. All right. Now, the other three trig functions. Well, what are the other three we always put on the right?
Cosecant, secant.
Cosecant, secant, and cotangent. And what's always the connection between them?
They're flipped.
They're flipped. So what do you think the cosecant is?
Hypotenuse over opposite.
Yeah. Cosecant is hypotenuse over opposite. What do you think the secant is?
Hypotenuse over adjacent.
That's going to be hypotenuse over adjacent. And cotangent, what do you think that one's going to be?
Adjacent over opposite.
Adjacent over opposite. So cotangent is adjacent over opposite. So I know a lot of people said they've heard of Sakatoa, but have you heard of Choshikow?
Never heard of it.
No, I don't really think I've heard of that one either. I just tried it. And that's what you get. You get Choshikow. I'm going to stick with Sakatoa. And then just remember I flip them. Or if you want to be on the cutting edge, you can go with Choshikow. Choshikow is the new Sakatoa.
Choshikow. I like the one.
Alright, Choshikow. Alright. So there's our six trig functions. All in terms of one side of the triangle divided by another side. Any question on those definitions? All right, well, let's try something. I want to find the 6 trig functions of theta. Now, let me kind of be clear. I am not looking for theta. We're going to do that tomorrow. I don't want you to tell me theta is 23.4 degrees. Not what I'm looking for. I'm looking for what is the sine of theta. What's the cosine? What's the tangent? Cosecant, secant, cotangent. At no point in this problem are we ever going to be finding theta. We could, but that's not what we're doing. Okay, we're writing the 6 trig functions. Now, let's see. What do you notice before I try to start writing all 6 of them down? What do you notice about my triangle? Yeah.
You have a length for your hypotenuse.
Right, I'm missing the hypotenuse. So, any trig function that has hypotenuse in it right now, that's a problem. I can do tangent and cotangent with what I know, but I'm missing the hypotenuse. How am I going to get the hypotenuse in that triangle?
Pythagorean theorem.
Yeah, we're going to do Pythagorean theorem. So we can just call that C for now. And what would be the equation I would set up?
A squared plus b squared equals c squared.
All right. And what about if you fill in the numbers that I have?
3 squared equals 4 squared equals c squared.
Okay. And 3 squared is how much?
9.
And 4 squared? And that gives you 25. And then what do you have to do on both sides?
Square root.
Yep. Take the square root on both sides. Square and square root cancel, just like sine and inverse sine. They're inverse functions. And what's the square root of 25? 5. Okay. So now that we know that, we can label that side as 5, and we can figure out all 6 trig functions. Now, we were lucky that came out to a nice number. If that was like the square root of 19, okay, there's nothing we would have been able to do with it. We would have just left it as square root of 19. But that also means if you have a side that's a square root, what are you not allowed to do with square roots in the final answer? Right. So if you had a problem like, let's say that was your opposite over your hypotenuse, you can't leave the square root of 19 in the bottom. Okay, that's not going to happen this time because we didn't get a square root. Okay, but you'd have to fix it, just like we learned earlier. Okay. All right, so let's go through it. Let's start with the sine. What's my definition for sine?
Opposite of the hypotenuse.
Yep. And what's the opposite in this case? And the hypotenuse?
5.
There you go. 4/5. Right. What's our definition for cosine?
Adjacent over hypotenuse.
And what's the adjacent?
3.
And the hypotenuse? 5. Okay. What about the definition for tangent? Yeah.
Opposite over adjacent.
Yep. What's the opposite?
3. Oh, 4.
4. And what's the adjacent?
5. No, 3. Sorry.
All right. Could you say it one more time for me?
3 is the opposite, right? Or is it 4? No, it's 4. Never mind. I take back my answer. I go somewhere else. I can't do this.
Okay, what help?
4 over 3.
4 over 3. Opposite is the side that's furthest away. Adjacent is the side that's right next to the angle. So 4 over 3. Now, once we have the 3 on the left, we know that the 3 on the right, we just take all of these and do what? Okay, we just flip them. So what's the cosecant?
5 over 4.
5 over 4. The secant?
5 over 3.
5 over 3. And what about the cotangent?
3/4.
3/4. And we've answered the question. Those are the 6 trig functions of that angle. Any question how we got those? Okay, we can look at any of them. Let's just look at the first one. Sine theta equals 4/5. Let's say that you did want to figure that angle out. To get this angle by itself, right now, it's an argument to the sine function. You'd have to get rid of the sine function. How could you get rid of the sine function from the left-hand side?
Inverse sine.
Yeah, you take the inverse sine. And this is exactly what I showed you today. But if you do it on the left, what else do you have to do?
Do it on the right.
You have to do it on the right. Inverse sine and regular sine cancel each other out. But we've got to be careful. Technically, they only cancel out if this angle is between 2 certain numbers. What were the 2 numbers that we said it had to be between? when the inverse was on the outside?
Negative 90 and 90.
Negative 90 and 90. How can we already be guaranteed, we don't even know the answer yet, but we can be guaranteed this angle is between negative 90 and 90. How do we know that? Why couldn't it be 92? Yeah? How come this is going to have to be between negative 90 and 90?
Because it cannot be greater than 90 because it's an acute angle.
Right.
It cannot be lower than 0 because it wouldn't be a triangle.
Yeah. This angle has to be, even we can guarantee this angle is between 0 and 90. Because we know it's between 0 and 90, you can do what I just did. You can cross those two things out. And then we could type that in on the calculator. Inverse sine of 4/5. And we could figure out what that angle is. I'm not interested in doing it right now, but we could. Okay. So any question on that?
Scroll down for a second.
We're going to talk more about that tomorrow, but because we talked about the negative 90 to 90 today, it was a good spot to tie it in. Okay. Actually, we already said this. Somebody said it earlier.
Mm-hmm.
What are complementary angles? Yeah.
Your angles that add up to 90.
Right. They're angles that add up to 90. And I think we already answered the next question. Or we already mentioned this. The two acute angles in a right triangle are always complementary. So if that's angle 1 and that's angle 2, we already said that they have to be complementary because all the angles add up to what?
180.
They all add up to 180. So angle 1 and angle 2 better add up to 90. Well, they're not all going to add up to 180. So we kind of already mentioned that. All right, so when we label angles that we don't know in trig, we don't usually use a number and then put a circle around it. I just called it angle 1 and angle 2. What kind of letters do we normally use?
X and Y.
Not for angles. We usually use special letters for angles.
Theta.
Theta. What kind of letter is that?
It's a Greek letter.
It's a Greek letter. So a lot of times when we have angles we don't know, we use a Greek letter. So the diagram that you use to draw a triangle, and you don't know anything in a triangle except the right angle, you use A, B, and C. So you use English letters for the sides, and you use Greek letters for the two angles you don't know. What is that Greek letter?
It's a fish.
It looks like a fish.
Is it lowercase?
That is lowercase. Yep, these are all lowercase letters.
So lowercase e and a lowercase p.
Would that be A
I don't
and
know.
B?
Well, it's a Greek letter. It's not an English letter.
Oh,
My lowercase a would look like that. It would look a little different. That is lowercase, but it's Greek. What is? Anybody know what it is? Yeah,
Alpha.
that is alpha. A-L-P-H-A. Okay, that's lowercase alpha.
capital on the top.
Capital alpha just looks like an English A.
Is that beta?
That one is the lowercase letter for beta. Capital beta looks like a capital B in English.
I swear, I thought lowercase alpha looks like an A.
No, it looks like that. I mean, some people may make it, a little bit more like that.
It's actually
But it looks like that. Yeah. And the reason why we use English letters for sides and Greek letters for angles, so there's no confusion. If I say, what'd you get for alpha? You know I'm talking about an angle. If I say, what'd you get for B? You know I'm talking about a side. Some textbooks will use capitals and lower cases. To me, that gets confusing. Yeah. Yeah. Okay, first of all, some capital letters and lowercase letters look the same. So if I put this, like if I Find C. Well, I can't really tell. Is that a capital C or a lowercase c? So we don't even do stuff like that. Okay? So that's the diagram we'll always use to solve triangles.
You don't make the argument that says find sigma.
Find sigma.
Yeah, sigma's letter also looks like a C.
Yeah, I don't remember what a lowercase sigma. I know capital sigma looks like this. That's
Yeah,
capital.
there's another way of writing it. It's just a C and then a smaller C.
Yeah. All right, let's write this down. Sine of alpha. Now, it's not going to be numbers, it's just going to be letters. So using the definition of sine, okay, opposite over hypotenuse. What's the sine of alpha going to be?
A over C.
Opposite over hypotenuse. Alpha is the perspective that you're looking at everything from. A over C. Okay. Now, I'm going to do something different. What angle is complementary to alpha in that picture?
Beta.
Beta. We said that these two angles are complementary. All right, so let's do something with beta. But what I'm going to do is I'm going to put the word co in front of that one that I just did. If you put the word co in front of sine, what do you get?
Cosine.
Cosine. Yeah. Cosine. What's the definition of cosine? Yeah.
Adjacent over hypotenuse.
Adjacent over hypotenuse. So from beta, what side is adjacent?
A.
A. And what's the hypotenuse?
C.
C. So what do you notice about the sine of alpha and the cosine of beta?
The same.
Yeah, they come out the same. In fact, co, I don't know if we've mentioned this yet, but co stands for complement of. So the full name of this is the complement of sine function. And that's exactly why they come out the same. This is the sine of the angle. This is the complement of the sine of the angle. And they always come out the same. Let's do another one. Let's do tangent of alpha. Okay. Tangent is opposite over adjacent. Now, instead of doing the tangent, let's do the tangent of the complement. Okay, call that cotangent. Cotangent stands for the complement of tangent. So the cotangent. And what angle is complementary to alpha?
Beta.
Beta. Cotangent is adjacent over opposite. What side is adjacent to beta?
A.
A. What side is opposite beta?
B.
B. Comes out the same again. So the way I matched these functions up, these are called cofunctions. Okay? Not reciprocal functions. That's when you flip one to get the other. Cofunction is when you put the word co in front of the trig function. So what do you think the cofunction, well, you already did it, but what do you think the cofunction is for sine? Cosine, complement of sine. What do we call the function that's the complement of secant?
Cosecant.
Cosecant, complement of secant. And what's the function that's the complement of tangent? That's called cotangent. Those are the only three pairs of cofunctions that you can have. So this and that are cofunctions. And what kind of angles are alpha and beta? They're what? They're acute, but together they're complementary. So these were cofunctions. These were complementary. anytime that you have co-functions and the angles are complementary, you're going to get exactly the same answer. They will be equal to each other. So, co-functions of angles that are complementary always come out equal. A over B, A over B. And that's called the complementary angle theorem. So let's see if we can try it with these numbers. Sine of 30. So think in your head, what's the co-function of what I just underlined? And what's the complement of 30? And that's going to be what's under that box. So what do you think the sine of 30 is the same as?
The cosine of 60.
The cosine of 60. Yep. How about tan of 15?
Cotangent of 75.
Cotangent of 75. Yep. It doesn't tell me what the tangent of 15 is. Like, I don't know the answer, but I know something else that's the same as that answer. That's the important thing. You'll see in a second. How about secant of 40?
Cosecant of 50.
Cosecant of 50. Yep. Okay, so what does that help you do? Let me show you. Okay. I want you to simplify the sine of 15 divided by the cosine of 75. Okay. Let's start with sine and cosine. Sine and cosine are what kind of functions?
Co-functions.
They are co-functions. 15 degrees and 75 degrees are what kind of angles?
Complementary.
Together they're complementary. So we have co-functions of complementary angles. That means that what's in the top of the fraction and what's in the bottom of the fraction are equal. So what would we get?
1.
Yeah, we would get 1.
Mr. Hager doesn't play horse.
Yeah. Because we're dividing two things that are the same. Now, if that was sine of 16 over cosine of 75, that whole thing's messed up. Yeah, now we need a calculator. So this is a theorem that works in a very, very specific situation. Right. How about this one? Tangent 12 minus cotangent 78. What are tangent and cotangent?
Functions.
What kind of functions?
Co-functions.
Co-functions. Okay, we got that part. What about 12 and 78? What do they add up to?
90.
90, which means they are?
Complementary.
Okay, we got co-functions of complementary angles. So what does that mean about what's in the green box and what's in the red box?
Equal.
They're equal to each other. So when you subtract two things that are equal,
0.
0. Okay, does it matter what two things you subtract if they're equal? Will you always get 0?
No.
So are there two things you could subtract that are equal
Oh,
and you don't get 0?
False.
No. You always get the same thing. You subtract two numbers that are the same, you always get 0.
Even if
2
it's
minus 2, 6 minus 6, 30 minus 30. It's always going to be 0. Does that work with addition?
no.
Like if I add 2 plus 2, is that the same as 5 plus 5?
No.
It's not
No. So when you add two things that are the same, you get what you started with doubled. Well, that all depends on what you started with. Okay, so this trick wouldn't work with addition. How about multiplication?
No.
No. It works with division. If you divide 5 by 5, you get 1. 8 divided by 8, 1. But 5 times 5, 8 times 8, those are different answers. So if you multiply two things that are the same, you get what you started with squared. Okay, so it doesn't work. All right. Any questions on those? Yeah.
Well, if you minus infinity by infinity.
Well, those aren't numbers, so that's a little different.
Oh.
All right. So that's 3-1 and the first part of 4-1. Okay. So homework from the first part, that's the yes or no questions, and the second part is more like the Socrates and the complementary angle theorem stuff. Okay, so those are the homework pages for tonight. Tomorrow we'll finish up 4.1. You've got just about 15 minutes left.